Imagine you have a box, and on this box is a very, very special lock. Here's the trick. Anyone, and I mean anyone, in the world can snap it shut. But only one person has the key to open it. And that person is you. It sounds like straight up magic, right? Well, this impossible lock is real. It's digital, and it's pretty much the only reason your online life is secure. Today, we're going to pull back the curtain and see how it's built. Not with some futuristic tech, but with some surprisingly elegant 18th century math.
Okay, so let's just get right to the heart of the matter, with the one question that everything else hinges on. How do you send a secret message to someone you've never met, knowing full well that every single word you send can be intercepted and read by anyone who's listening in? This isn't just a fun little riddle. It's the fundamental problem that we had to solve to build an internet we could actually trust.
And the solution is that impossible lock we were talking about. The technical term is asymmetric cryptography, but all you need to know is this. Instead of one key that everybody shares, you now have two completely different keys. There's a public key that you can shout from the rooftops, give it to everyone, that can only lock the box. And then there's a private key that you keep secret, which is the one and only thing in the universe that can unlock it.
Now, for basically all of human history, this idea would have sounded insane. You know, from the ancient Spartans all the way up to the famous Enigma machine in World War II, encryption was always symmetric. That just means you and your contact needed the exact same key to both lock and unlock a message. The massive glaring weakness? Well, you had to somehow get that key to the other person safely in the first place. This is famously known as the key exchange problem. And this is the breakthrough. The old way, symmetric keys, was totally haunted by that key exchange problem. But the new way, asymmetric keys, it just sidesteps the whole issue. You've got a public key for locking and a totally separate private key for unlocking. The problem isn't just solved, it's made completely irrelevant. So how in the world do you create two keys that are mathematically tied together like this? Well, you might think the answer came out of a computer lab in the 1970s, but you'd be wrong. It actually comes from way back in the 1700s, from the brilliant mind of a mathematician named Leonhard Euler. Turns out, the secret to our modern digital security was just sitting there, hidden in a quiet little corner of pure number theory for centuries. So, let's meet the hero of our story, Euler's phi function. I know, it looks a little intimidating with that Greek letter, but the idea is actually super simple. For any number you pick, let's call it n, the phi function just counts how many smaller numbers don't share any factors with it other than the number 1. That's what coprime means. That's it, seriously. All right, let's make this concrete so you can see it in action. Take the number 10. Its factors are 2 and 5. The numbers smaller than 10 that are coprime to it, the ones that don't share those factors, are 1, 3, 7, and 9. There are 4 of them, right? So phi of 10 is 4. Simple. Now look at a prime number, like 7. All 6 numbers below it are coprime, so phi of 7 is 6. And that reveals a really useful pattern. So the crucial point is that we don't have to sit there and count every single time. There are these beautiful little shortcuts. If a number p is prime, phi of p is just p minus 1. And here it is, the formula that makes our entire digital lock possible. If your number n is made by multiplying two different prime numbers p and q, then phi of n is just p minus 1 times q minus 1. Remember that formula. It is the secret sauce. Okay, so we have our secret component, this awesome phi function. Now let's see how we actually use it to build the encryption machine, step by step. This is the famous RSA algorithm, named for the guys who invented it, Rivest, Shamir, and Adelman. Think of it like a 5-step recipe. First, you pick 2 absolutely massive, random prime numbers, p and q. Second, you multiply them together to get your modulus, n. Third, and this is the key part, you use our secret formula to calculate phi of n. That value is the core secret. Fourth, you pick a public number, e. And finally, you use that public e and your secret phi of n to calculate a private number, d. Okay, theory is great, but let's actually see it work with some numbers we can wrap our heads around. We'll pick 2 prime numbers, p equals 61 and q equals 53. Just keep in mind, in the real world, these numbers would have hundreds of digits each. First up, we calculate our modulus, n. Super easy. We just multiply our 2 primes together. So 61 times 53 gives us 3,233. This number, n, is going to be part of our public key. Everyone is allowed to know this. And now for the magic. We calculate phi of n using our special shortcut. 61 minus 1 times 53 minus 1.
That's just 60 times 52, which gives us 3120. This number, this is our trapdoor. This value must be kept absolutely, completely secret.
For the next step, we just pick a public exponent, e. It has to be co-primed to our secret 3120, and a super common choice is just 17. Then, we do a final calculation involving that 17 and our secret 3120 to get the private exponent, d, which in this case turns out to be 2753. And bam, we have our keys. The public key is the pair of numbers 323317. And the private key, which you guard with your life, is 32332753.
So why is this secure? I mean, why can't someone just take the public key and work backwards to figure out the private key? Well, the answer lies in something mathematicians call a trapdoor function. It's a process that's incredibly easy to do in one direction, but nearly impossible to reverse unless you happen to have a secret piece of information. And here is that trapdoor in action. If I give you the numbers 61 and 53 and ask you to multiply them, you can do it in seconds. That's the easy direction. But now, let's go backwards. If I only give you the number 3233 and ask you to find the two prime numbers that multiply to make it, that's much, much harder. And when we're talking about the 600-digit numbers used in real encryption, that factoring problem is considered completely impossible for even the most powerful computers on Earth. So here's the bottom line. The entire security of this whole system rests on one thing: how ridiculously hard it is to factor that public number n. Because if you can't factor n back into p and q, then you have no way of finding our secret value, phi of n. And if you can't find phi of n, you can never, ever calculate the private key d. Everything is locked behind that one single hard math problem. And what actually makes the keys work? What guarantees that the math checks out? It's another little piece of Euler's genius, a rule called Euler's theorem. It is the mathematical promise that, because we built this whole system using our secret phi of n, any message scrambled with the public key E will be perfectly cleanly unscrambled by the private key D. It's pure mathematical magic. Okay, so that is the beautiful, clean theory. But when you're actually buying something online or sending a secure message, things are a little bit more complex. The textbook version of RSA that we just walked through, well, it actually has a few practical weaknesses that we need to patch up. For one thing, if you just use the raw formula, encrypting the word attack will always spit out the exact same string of encrypted gibberish. An eavesdropper could totally spot those patterns. Even worse, a clever attacker could actually modify your encrypted message without even knowing what it says. These are really serious flaws in a real-world system. So how do we fix this? Well, the solution is surprisingly simple, and it's called padding. Before your message ever gets encrypted, a block of carefully structured random data gets added to it. This makes sure that even if you encrypt the word attack 1,000 times in a row, you're going to get 1,000 completely different encrypted results. This one simple step makes the whole process tough enough for the real world. And that really brings us to the core takeaway here. The security that holds up our entire digital society, all our banking, our private conversations, our online identities, it isn't built from concrete walls or giant steel vaults. It's born from the abstract, elegant difficulty of a problem in pure mathematics, one that was first explored more than 200 years ago. But that leaves us with one final, kind of scary question. This whole system, this whole digital world, it relies on a math problem being too hard for our current computers to solve. But what happens when a totally new kind of computer comes along? A quantum computer that's specifically designed to solve exactly this kind of impossible problem. The race for the next generation of impossible locks is already on. Thanks for watching.